Okay, I wanted to briefly go over this chapter. There'll only be one video for this chapter. But let me start talking about some of these unit cells. The first all, so let me talk about simple cubic. So imagine, like, think about boxes. I think about shoe boxes. So if how many at single corner, how many shoe boxes can you stack up? Well, the thing is, you can stack up eight shoe boxes, right? There's four on the bottom and then four on the top. So if you picked an atom, a sphere, and you put it on a bunch of boxes, that sphere will be divided up in 1/8 of those each of those shoe boxes, if you will. So right, four on the bottom and then four on the top, each of those corners there. So I guess I should back up. Why are we doing this? Well, spheres are kind of hard to work with. We like the Cartesian coordinates, the x, y, z coordinates, so we tend to think things in boxes. That's how our number system works better that way. I mean, yeah, we can use spherical coordinates, but we just do better with Cartesian. So we make these mythical unit cells to make things better. And the simple cubic just has an atom on each of the corners of a box, the cubic box. So each of those has 1/8 of an atom. So a simple cubic has the packing efficiency of here is 52%, but it's not very good because it just has the corners. Then you have a body-centered cubic. Body-centered cubic is the same thing as a face-centered cubic, except in the center of the box is a whole atom. Then we have a face-centered cubic. Face-centered cubic has an atom on each of the faces. Each of the faces is like having a half an atom, and there are six faces to a box. And so if each of those faces, or six faces, each one has half a phase, half an atom, half a phase, half an atom. Those are six times a half is three, and then you get one from the corner. So the face-centered cubic has a much greater packing efficiency. So what? Why do we care? Well, different elements are going to have, and different structures are going to have different of these different types of structures depending on temperature and also what it is. Iron, for instance, iron tends to be at a face-centered cubic, but at 900 degrees Celsius, it changes to a body-centered cubic. So, and we use that for a couple things. So there's a process called austenization. That's a German word. Austenize. It means quenching. So if you ever seen movies where they're like making swords or something, you'll see people throwing swords in fires and hammering it, and all the sparks are flying, and they stick the swords in water. Why are they quenching the swords? What are they doing to the iron? You're switching from body-centered cubic to face-centered cubic really quickly. And why do you do that? Well, because, so here I'm showing this picture here. You want to make steel. And the way you make steel is you put carbon in with the iron, and then if you can see these different, they have blue as I'm having with the iron, and then there's black. The black is the carbon. The black carbon gets stuck when you quench it, and it makes the iron much more rigid. That's what steel is. And this was found out actually by practice for samurai swords. Samurai sword. There's my picture of a samurai sword on the bottom there. It has these ribs on it. The ribs are actually iron carbide. So iron carbide is an ionic compound. It's very brittle, but it's very strong. And steel. So steel is very bendy. So what the samurai swords do is they have these iron oxide ribs in them, makes it a very strong sword. So the Japanese figured out how to do this by trial and error over time. Now of course we know what it is going on, but they had to hand lay each of those layers of steel and iron oxide onto the swords. So they're very hard to make. So okay, we don't necessarily have to do cubics. We can use hexagonal closest packing instead. So iron, for instance, has face-centered cubic and body-centered at 900 degrees Celsius. Platinum, for instance, platinum shows hexagonal close packing. So it depends on the elements and what the compound. Also, compounds can have these. It really just depends on what they have. So that's the okay. So let's move on and talk about melting points. So, melting point is a show of how strongly bound something is. So, something that has a very low melting point means that there's not very much attraction. Sometimes a high melting point means that there's a huge amount of attraction. So, let's start with molecular solids. So, molecular solids and water, for instance, would be a molecular solid. These, generally speaking, have low melting points. So the intermolecular forces are not super strong. Ionic solids, on the other hand, moving across, have much stronger bonding, and these have really high melting points. So, like table salt here, have you seen ice melt? Have you ever seen salt melt? Have you ever heated something up high enough that salt is going to melt? I've never seen salt melt. So that's one thing. And it'll melt. It just has to be really high. Then atomic solids. So let's talk about, we have non-bonding, metallic, and network covalent. So non-bonding, these are things like the noble gases. So things like xenon here. These have extremely low melting points. So these do not. It's not that hard. They have London dispersion forces only, and they're very, very weak. Then metallic bonds. Metallic is held together by metallic bonds. These have various melting points. There is no trend. There's no periodic trend whatsoever. So you can have metals that have very low melting points, like mercury and cesium, and you can have metals that have very high melting points, like platinum and thorium. So there is absolutely no trend. And then you, of course, have the middle. I mean, platinum is right next to gold, and gold has a medium, relatively low melting point. I mean, it's not super high, it's not super low. Platinum is really high. There's no trend whatsoever. Then network covalent. These are things held together by covalent bonds. So diamond is one, or graphite. Both of those are covalent network for carbon. So silicon dioxide has the SiO4 tetrahedron network. These have very high melting points. So again, this is the attraction within the molecule there. Okay, and let me talk about. Here's benzene and toluene. So I've drawn it this way. And there is a break in here. Benzene has a melting point of 5.5, and toluene has a melting point of close to negative 100 degrees Celsius. Generally speaking, though, the more massive something is, the higher the dispersion forces. Why is toluene different? It has that kink in it. It has that extra edge, and because of that, it's harder for toluene to form a really good network solid, whereas benzene, it's easy. It's a honeycomb. It can kind of, it's a hexagon. It can really link together very well. And so this is more. It's kind of like oh, that's the reason why it is. And one thing I think you as my students and my students in general, like, oh, Mike tells us something, a rule, and then he tells us an exception to the rule, and there's an exception to the exception to the rule. And that's one thing about chemistry, is that there's all these exceptions to the rule, and overall it makes sense. But it's interesting. It's interesting. I think it's kind of cool. That's the reason why I'm including this in the discussion. They're like, okay, this explains a little bit more about forces and why things work the way they do. So that's interesting. Okay, and let me talk about some other things. So remember we talked about molecular orbital theory in last semester. So if you have a lithium atom, you have the atomic orbitals, and if you have two lithium, you're going to have the bonding sigma Gerada bonding orbital, and you have the sigma star Ungerada anti-bonding orbital. And with the dilithium there, you will have the electrons populated in the bonding orbital, and the bonding orbital there is also known as the HOMO, the highest occupied molecular orbital, and the sigma star in this case is the LUMO, the lowest unoccupied molecular orbital. Now, if you have three lithium atoms, you get more molecular orbitals forming. Four atoms, you get different ones. And why these form? From last semester, the electrons and the protons come together, and the electronic magnetic fields of the protons and electrons form molecular orbitals, and the atomic orbitals go away. Now, if you have lithium metal, you have a band of occupied orbitals and you have a band of empty orbitals. And then the Fermi level, that is the highest, is similar to the highest occupied molecular orbital. So for a conductor, and lithium metal is a conductor, the conduction band is touching the valence band. And then if you have a big difference, so I'm drawing on the right here, those two boxes, this is known as an insulator. The occupied orbitals have a large difference between the empty orbitals. So this is an insulator. So right here, the fact that the energy has to jump up. Can insulators conduct electricity? Yes, they can. So humans, we are insulators. Apparently, it takes us about 60 volts. So apparently, if you put a potential of 60 volts across humans, we will conduct electricity. Unfortunately, we are also resistors, so that will cook us as well. So, but humans tend to be insulators. Then you have in between a conductor and insulator, a semiconductor, a sort of conductor like silicon. Silicon's band gap is about 5 volts. So you have a metal that there is no difference between the valence band and conduction band. You have humans that ours is about 60 volts potential to conduct, and then you have silicon has potential to conduct is 5 volts. So it doesn't take much for silicon to conduct, and we use silicon as our zeros and ones. So conducting electricity, that's a 1, and not conducting, that's a 0 for our binary code. Okay, let's go back to lithium. And what we find out there, though, is that as you go to higher numbers of lithium atoms, so on the order of thousands of lithium atoms, you get these phases in between the bulk material and then the molecular orbitals, and you get what we call quantum dots. And you get bands, and you have band gaps, and you have bands of things. And so this is something that's weird that we're still trying to figure out what's going on. And the so what with this is that our transistors that we make for our computers, silicon transistors, if we go any smaller on them, then we've reached the quantum dot phase, and it messes up the band gap. So we can make smaller transistors, but they don't work the same because they start having these different bands rather than the 5 volt bulk band gap, and that's why if you've noticed that we now have like the computer processors now have like quad core, 8 core, 16 core, 32 core, where they're just increasing the number of the processors they have in there because they can't make the transistors smaller, at least not with our current computer programming. If we can figure this out mathematically and do more research, then we could make them smaller, but we can't right now. So it's interesting. It's interesting the way that we do this, and a lot of it is we don't know. The way that we make so the way we make these processors, it's you take sand, silica sand, and you melt it, just carbon reduction of that, and you get what's called metallurgy grade silicon. Then you take that and you chemically treat it to get electronic grade silicon. You take the electronic grade silicon and you cut these, they usually have rods, and you cut them into wafers. And then you take the wafers and you press on an oxide layer onto the silicon. And then you put that into a chamber with fluorine gas and ultraviolet light. And we believe what happens is that the ultraviolet light and the fluorine gas turn to hydrofluoric acid, and it eats away the silicon that's not covered in oxide. Then we take off the oxide layer, and then you have the transistors for the computer processor. So that's how we make them. And those wafers they're worth a lot of money after you make them. There's a lot of processors on there, and it's not an easy thing to make, and so they're very, very valuable. One of the reasons why we don't understand it, well, a lot of this is trade secrets to the semiconductor business. They don't like talking about it that much because of trade, like I said, trade secrets. And the other thing is when you're working with fluorine is just so reactive. They have to change the vessels every once in a while because the fluorine just eats through them. So because of that, trying to do scientific tests on these things, it just destroys any equipment. The equipment that you work on does not last very long. So you have something that eats through your stuff with a industry that doesn't want everyone to know what's going on. So because of that, we don't have that much knowledge. And I mean, a lot of government sponsored research, we'd rather reuse our stuff rather than just continually having to replace it. So because of that, studying this has been put on low priority. I want to look at other things instead. So, but it's interesting. I think it's interesting the way that we do things and where we're at. So this is kind of like, hey, where are we going with science? And that's kind of where we're going right now, is trying to look at this quantum band, these quantum dots, and see what the heck's going on there, because we don't know what's going on. And we that already has implications with the semiconductor business and how we do we do make things like electronics. Oh, and this is what I described before, semiconductor and conductor kind of thing. So, and last thing I'll talk about are plastics. So polymer. Well, I guess I even said plastic. What is the definition of plastic? Something is plastic if it's moldable when it's molten. So, I mean, we say plastic, we really think of polymers, but metals are plastic. So, because they're moldable when they're molten, right? So, but plastics, you can mold them when they're molten, and the one by far that we use the most of plastic is polyethylene. And okay, so polyethylene is an addition polymer. What does that mean? It means you just add. So here is ethylene here and drawn in the blue and Lewis structure. That's ethene, ethylene. Ethylene is the common name for this. And if you get it to react, you form polyethylene. You have the line. It's just a really long hydrocarbon, and that is by far the most common plastic polymer that we have, and we use it for everything. And we can have some other addition polymers. So polypropylene, these are a little bit tougher. So some kitchenware, for instance, use this. And polystyrene, of course, I think mostly styrofoam is from polystyrene. So, and these words polyethylene, many ethylenes, polypropylene, many propylenes, polystyrene, many styrenes, and polyvinyl chloride. So then the PVC, polyvinyl chloride, also known as PVC. This is used as a little bit more sturdy. Then there's if there's two chlorines on it, that's the polymer of that is known as Saran. So polyvinyl chloride. So Saran. That's two chlorines, and like Saran wrap, for instance. So there's more than just these. Condensation polymers. These are ones that you when they polymerize, when the units come together, a small molecule pops off. Most often, that polymer is water. And for us, in our human bodies, proteins are condensation polymers of amino acids. So when amino acids join together, water pops off. And likewise, in digestion, you have to add water into the bond to break the protein bonds, to break them down to their subsequent amino acids. So here are some of these. So polyurethane, for instance, use this for I use this to coat like wood sometimes. So the polyurethane. And you can also see the R group there. The R group means a hydrocarbon. So it just means a certain. It could have, in this case, the example could be 2 carbons. It could be 20. It could be 21. It could be 50. It just depends, and they're gonna have different properties each time you change it. So polyethylene terpathylate. So polyester means many esters. An ester. This is right here, the ester group. You have a carboxylic, so this is a carboxylic acid group, the C double bond O. And if this was an OH, if this was an H, this thing circled in red there would be a carbonic acid. Anyways, carbonic acid, so that would be an acid group. And if you put a a hydrocarbon on that, that's known as an ester. And esters are nice because they smell really good, and a lot of our fragrances and flavors are esters. And also biodiesel is an ester. So that's a many polyester, many esters. So we use these for the thing. And this is soda bottles. A lot of times has polyethylene terephthalate, also known as PET, PET. So and also you can use it to make clothing, of course. And nylon. Nylon is a condensation polymer. Nylon is about as close as you can get to protein. One thing about nylon, though, and polyester too. Polyester, well, and any plastics, they melt, right? I mean, plastic means that it's moldable when molten, and if you're wearing nylons and you get around a heat flame, they can melt. I remember this when I was working. I took an art class at Manoa, and we were working with molten bronze. And I remember one of the students was wearing some nylon jeggings. The teacher's like, "Yeah, that's bad. You cannot get close to the molten the molten bronze there. If any molten bronze hits that, that's gonna catch on fire and it's gonna melt and it's gonna stick to your legs." So, because the teacher told us we need to wear jeans, and so someone came in jeggings and nylon jeggings, and cotton jeans are different than nylon jeggings. So be careful about using these things around around heat, especially. But nylon, among other things, is also used to make bulletproof vests. So nylon is a tough material. It's a really tough material. So, and it really just depends what your application is, and you got to be careful about that. And like some things you don't even think about, like nylon. So I mean, don't wear them at chem lab. I mean, in a way, it depends on what you're doing. So if you're using a Bunsen burner, don't wear nylons. If you are doing something that maybe working with just acid, then a nylon's okay because they're fairly water resistant, so it would bounce off. But be careful of that. But these polymers, they have many uses. So, and and of course, the source for our polymers is petroleum. So petroleum is our starting material for a lot of these things. And if you think about something, can you think of any product that you buy? So 10 gallons of gasoline. So at the time I'm making this video, it's about $3.20 at Costco. So let's say $3. Let's see. Okay, so can you think of anything that weighs 60 pounds that costs $30? Can you think of anything you can buy in the store that weighs that much? So it weighs 60 pounds, you can buy for $30. And if that's really cheap, right? I mean, if you buy plastic furniture, I mean, you're gonna be dropping like $200 or $300 for crappy plastic furniture for 60 pounds of that, right? But gasoline, that's only $30 for that 60 pounds worth. So that's it goes to show you how low of value fuel is, whereas polymers are a relatively high value product. So, but I think it's interesting. But, well, and okay, well, this is all I really want to say for this chapter. Join us next time for more chemistry.